What we are going to be talking about today is Thevenin and Norton equivalent circuits. These are summarized by two theorems. So we are going to start with Thevenin's theorem. So Thevenin's theorem states that any linear electrical two-terminal network replaced at the terminals by an equivalent voltage source VTH in series with an equivalent resistance RTH. It goes on to define the equivalent voltage VTH is the open circuit voltage measured at the terminals of the live network and the equivalent resistance RTH is the resistance seen between the terminals dead electrical network. We're going to talk about what live networks and dead networks mean here in just a moment when we work an example. Dead, let me write that better. So we are going to analyze the circuit and we are going to determine the Thevenin equivalent of this circuit. So our circuit of interest will be this guy where we have a 10-volt source connected to a 10-ohm resistor. Here is a 5-ohm resistor. Here is a 1-amp source. And here are a pair of terminals. So Thevenin's theorem effectively states that we can replace this 4-element network, and it could be a more complicated network than this, but this particular example has 4 elements. We can replace this 4-element network with an electrically equivalent practical voltage source. Okay. where our practical voltage source will be composed of a voltage source VTH in series with a resistance RTH. And then Thevenin's theorem goes on to tell us how we solve for VTH and how we solve for RTH, okay? So I'm going to copy this network. And we're going to talk about finding VTH first. So Thevenin's theorem says that the Thevenin voltage is the open circuit voltage measured at the terminals of the live network. So we have these two terminals on the right-hand side. Our Thevenin voltage is simply the voltage drop across these terminals when the terminals are open circuited. How we find that voltage is completely and utterly up to us. We can use any circuit analysis technique that we care to use. So, for instance, we could use superposition here to find VTH. I say that because with the 10-volt source on and the 1 amp current source off, this is simply using voltage division to get VTH. With the 1 amp source on and the 10-volt source off, we would just use Ohm's law, and then we'd add those two results together. I believe we can just use Kirchhoff's current law at the top right-hand node and solve for VTH. We could do mesh analysis and solve for VTH, whatever we want to. So I would like for you guys to just throw out some sort of circuit analysis technique, and then let's run with that idea. Mesh. All right, Devarier, mesh sounds great. So I'm going to call this mesh current IA. I'm going to call this mesh current IB. And I'm going to call, actually, those are my only two mesh currents. I'm not going to have a mesh current on the right-hand thing because it has an open circuit, so the current's going to be 0. All right, so we don't have any dependent sources, so we don't need to write a controlling variable relationship. We do have a current source, so we can say that IB is equal to -1 amps because IB is flowing down as it flows through the current source, and the current source tells us that it's supplying 1 amp of current in the up direction. Now I can write my KVL equation around mesh A. And so that's going to give me -10 volts plus 10 ohms times IA plus 5 ohms times IA minus IB is equal to 0. And I'm going to solve this system of equations for IA and IB. We know that IB is going to come out to be -1 amp. So let me just find a calculator here and throw this in real quick. So this is a 2-equation, 2 unknown system. In my first equation, my coefficient for IA is 0. My coefficient for IB is 1, and my constant term is -1. In my second equation, my coefficient for IA is 10 plus 5 is 15. My coefficient for IB is -5, and my constant term will be +10 when I move it over to the right-hand side of the equal sign. And now when I solve these, I get IA is +1/3 of an amp, and IB is -1 amps. So now that I have these two mesh currents, what I can do is I can observe that, let me identify some nodes here real quick. So the voltage VTH is the potential difference between the red node and the blue node, which is the same as the voltage drop over the 5 ohm resistor. So from that, VTH is going to be 5 ohms times IA minus IB. So that's going to be 5 times 1/3 minus -1. Comes out to be 20/3 volts. So that is my Thevenin voltage. Okay. We did not have to use mesh analysis. We could have used any circuit analysis technique that we chose, but because Devarier suggested mesh, that's what we did. Now we're going to talk about finding RTH. So I'm going to make another, let's see, finding RTH. I'm going to make another copy of my circuit and put it down here. So Thevenin's theorem tells us that the equivalent resistance RTH is the resistance seen between the terminals of the dead electrical network. To make our network dead, we have to turn off our independent sources. We turn off current sources by replacing them with open circuits. So I'm just going to erase this guy. And we turn off voltage sources by replacing them with short circuits. So I'm going to replace my 10-volt source with a short circuit. And now we're going to look in through our terminals, and whatever resistance we see is our Thevenin equivalent resistance. In this case, it looks like 10 ohms in parallel with 5 ohms. Excuse me, 5, not 50, which is going to be 10 times 5, or 50 over 10 plus 5. So 50 over 15, or I believe that's the same as 10 over 3 ohms. So there's our Thevenin equivalent resistance. So putting those two results together, our Thevenin equivalent circuit is this guy, right? So I'm just going to paste this guy here. These two networks are electrically equivalent, which means they would deliver the exact same of voltage, current, and power to an arbitrary load resistance that was connected across those open circuited terminals. Okay, so the Thevenin equivalent circuit is an alternative way to get a practical voltage source representation of a network where simply doing source transformations may not be the best route to do that. Okay. Now let's talk about the Norton equivalent circuit. And we'll introduce that by going over Norton's theorem. Norton's theorem is incredibly similar to Thevenin's theorem, even though they were developed about 60 years apart. So Norton's theorem says any linear two-terminal electrical network can be replaced at the terminals by an equivalent current source I Norton in parallel with an equivalent resistance R Norton. The equivalent current I Norton is the short circuit current of the live network and the equivalent resistance R Norton is the resistance seen between the terminals of the dead electrical network. Which means the Norton resistance, R Norton, and the Thevenin resistance, R Thevenin, are literally the exact same quantity. So let's talk about finding I Norton. Looking at the exact same circuit that we were analyzing a little while ago, what we're going to do is simply short circuit our terminals and figure out how much current flows through the short circuit. The current flowing through the short circuit is, by definition, our Norton current. And we can determine this current however we choose to do so. So, how do you guys think we should find this current I Norton? So nobody's saying anything. So nodal analysis. All right, Justin. So using nodal analysis, I'm going to identify my nodes. So this is going to be one node. And this is my other node, okay? So this is going to be a little bit awkward here, but we can definitely get through it by realizing a couple of things, okay? So the first thing that I want us to look at here, this isn't going to be a strict nodal analysis here because we really only have two nodes. If we chose ground to be the bottom node, then that would tell us that the blue node is at 10 volts, which we could get just by looking at the circuit anyway. Okay. But what we're going to look at here, so there's a current of 1 amp that's leaving this 1 amp source. It's going to hit this green node and then it makes a decision. It could flow to the left and then flow down through the 5 ohm resistor. It could flow to the left and continue flowing through the 10 ohm resistor in series with the 10 volt source, or it can flow to the right, flowing through that short circuit. I would argue that all of the current from the 1 amp source is going to flow to the right through the short circuit. So I Norton is going to be 1 amp plus, we have some amount of current that's leaving the positive polarity terminal of the 10 volt source. It's going to flow through the 10 ohm resistor, and then it sees a path containing the 5 ohm resistor, the 1 amp source, and the short circuit. All of this current will also choose the short circuit path, where this current is given by, sorry, my screen is scrolling more than I want it to, 10 volts divided by 10 ohms. And so from this, I Norton is equal to 2 amps. Effectively, we just did superposition without doing all of the extra work of actually turning things off and on, okay? Now, what this means that since our Thevenin equivalent resistance is the same as our Norton equivalent resistance, we have a Norton equivalent circuit it's going to look like this. So let me paste this here. So here's our original. Our original circuit will be electrically equivalent to a 2 amp source in parallel with a 10/3 ohm resistor. Okay. What is interesting and hopefully also obvious is that since our Thevenin equivalent circuit is equivalent to our original circuit, and our Norton equivalent circuit is equivalent to our original circuit, the Thevenin equivalent circuit and the Norton equivalent circuit are also equivalent to each other. And in fact, they are simply source transformations for the same thing, right? So hopefully you guys paid attention in the video lecture for source transformations, wherein we said that we can convert a practical voltage source. So that would be some voltage in series with a resistance into an electrically equivalent current source. Or a current source in parallel with some resistance. And the rule here is simply Ohm's law. VTH must be equal to I Norton times RTH, or I Norton would be VTH divided by RTH, or RTH would be the ratio VTH over I Norton. All three of those equations really mean the same thing. They're just algebraic manipulations of Ohm's law. Sarah asked, if the I Norton current was negative, would you just flip the arrow direction in the Norton equivalent circuit? That's a very good question, Sarah. So in a circuit like the ones that we have analyzed today, where there are no dependent sources, what I've done is very intentional. Okay, let me scroll up here to our original circuit when we were finding VTH. Okay, so I found VTH with the positive polarity on top. And because of that, I defined I Norton as flowing down. So apparently the Norton current would be flowing into the positive polarity terminal, okay? It's very important that I do that, or I might get a negative Thevenin resistance. Now, on tomorrow's class, when we deal with Thevenin and Norton equivalent circuits that contain dependent sources, it is possible to get a correct answer that has a negative Thevenin resistance. But we should never see a negative resistance for a circuit that does not contain any dependent sources. And in fact, I will try my damnedest to make sure that you guys never experience a circuit that you'll analyze and get a negative resistance. For your homeworks and things like that, you're usually told which terminal to consider the positive polarity terminal when determining your Thevenin voltage. So you typically are told a reference polarity, and you're also typically told a reference direction for your Norton current. I make sure to do that on the exams as well. Was that a sufficient explanation, Sarah? All righty. So what I would like for us to do now is something slightly different, okay? We're still going to do Thevenin and Norton equivalent circuits, but we're going to find out how to deal with a case when we're trying to find the Thevenin equivalent with respect to a particular circuit element, okay? So let's say that our circuit element, or excuse me, that our circuit of interest is this guy, where we have a 32 volt source, and then we have a 10 ohm resistor, a 10 ohm resistor, a 15 ohm resistor, a 30 ohm resistor, and a 0.2 amp source. Now, we want to find VTH, I Norton, and RTH as seen by the 15 ohm resistor. So effectively what we're going to do is we're going to disconnect the 15 ohm resistor, and that's going to be the terminals where the 15 ohm resistor was connected that we wind up looking into, okay? So finding VTH, let me make a copy of this guy. So in order to find the Thevenin equivalent with respect to the 15 ohm resistor, we remove the 15 ohm resistor and it leaves behind a set of open circuit terminals. Our Thevenin voltage is the voltage drop across this open circuit set of terminals where the 15 ohm resistor used to be. Just for the sake of argument, let's put the positive polarity terminal on the the right-hand side, and the negative polarity terminal on, positive polarity on the right-hand side, negative polarity on the left-hand side. How might we go about solving for our Thevenin voltage? So let's do nodal analysis. So here's one node. Here's another node. Here's a node. And here's a node. Let's choose our bottommost node to be our reference. And then let's call this VA, VB, and VC. Since we have no dependent sources, we have no controlling variables to worry about. We have one voltage source, so we're going to have one voltage relationship to write. So we could say that VA is equal to 32 volts. And now we're going to write KCL at nodes B and C. So KCL at B tells us VB minus VA over 10 ohms plus VB over 10 ohms is equal to 0. And since we already know what VA is, we could actually just solve this guy and find that VB is going to be 16 volts. When we apply Kirchhoff's current law at node C, we're going to have VC over 30 ohms minus 0.2 amps is equal to 0, which we could solve, and we would find that VC is going to be 30 times 0.2, which is 6 volts. Now, how would we find VTH? VC minus VB, absolutely correct, Valerie. VTH is VC minus VB. So that is going to be 6 minus 16 is negative 10 volts. Now let's find our Norton current. So since we're finding the Norton current with respect to our 15 ohm resistor, we will remove our 15 ohm resistor and then we short circuit our terminals. Our Norton current will be directed to the left. How are we going to go about solving for this Norton current? Well, I say let's use mesh this time. Typically speaking, I use nodal analysis to find VTH because nodal analysis tells me voltages, and I use mesh analysis to find I Norton because mesh analysis is used to find currents. That's not to say that I won't do things like superposition, KCL, KVL, Ohm's law, things like that, if that's easier. But generally speaking, I typically use nodal analysis to find the Thevenin voltage and mesh analysis to find the Norton current. Right, so here's IA. Here's IB. Here's IC. We don't have any dependent sources, so we don't have to write any controlling variable relationships. We do have a current source, so our current relationship is going to be IC is equal to negative 0.2 amps. We're going to have to write a KCL equation for mesh A and a KCL equation for mesh B. So for mesh A, that's going to look like negative 32 volts plus 10 ohms IA plus 10 ohms IA minus IB is equal to 0. For mesh B, we are going to have 10 ohms times IB minus IA plus 30 ohms IB minus IC is equal to 0. And we will solve these three equations for IA, IB, and IC. So just going to put this into my calculator. All right, so in my first equation, I have 0 IA, 0 IB, 1 IC is equal to negative 0.2. In my second equation, I have 10 IA plus 10 IA, so that's 20. I have negative 10 IB. I have 0 IC. And I have positive 32 as my constant. In my third equation, I have negative 10 IA, 10 plus 30 or 40 IB, and then negative 30 IC, and that will be equal to 0. And solving, I find that IA is 61 over 35 amps. IB is 2/7 of an amp, and IC is negative 0.2 amps. How does I Norton relate to our mesh currents? I Norton is negative IB, absolutely correct. All right. Lastly, let's solve for RTH. All right, so we need to remove our 15 ohm resistor. And it's going to leave behind the terminals that we're looking into. We need to be looking at a dead network, which means our 32 volt source is off and our 0.2 amp source is off. So I believe that our Thevenin equivalent resistance, RTH, is going to be our 30 ohm resistor in series with the parallel combination of 5 ohms in parallel, 10 ohms in parallel with 10 ohms. Getting slightly ahead of myself there. Just to be clear about how I came up with that, let's label our nodes. So we can see that the 10 ohm resistors are in parallel because they share the orange node and the red node. And then I say that the parallel combination of 10 and 10, which is just 5, is in series with the 30 ohm resistor because that parallel combination occurring, so between orange and red, we see 10 in parallel with 10 is 5, and then between red and blue, we see 30. And that gets us from our orange node to our blue node, which is the terminals that we're looking in between. So this to me looks like 35 ohms. But we can check our answer, right? Our Thevenin resistance must be our Thevenin voltage, VTH, divided by our Norton current. Let's scroll up here. Our Thevenin voltage we found to be -10. Our Norton current we found to be -2/7. And if I divide -10 by -2/7, that's the same as multiplying -10 by -7/2. And I wind up getting 35 volts per amp or 35 ohms. So if we can find 2 and we're sure about how we did it, we can actually get the third quantity without doing any analysis whatsoever. Because as long as we know any 2 of VTH, I Norton, and RTH, we can always solve for the third quantity. All right, does anybody have any questions regarding Thevenin and Norton equivalent circuits without dependent sources? All righty, well, that's all that I wanted to talk about today with you guys. So I will just hang out in Zoom. If anybody decides they have a question while they're working on homework assignments and class assignments or anything like that, just let me know. Otherwise, I hope you have a great rest of your afternoon and I will see you tomorrow.